A pleasant day, everyone. Today, we'll be discussing about Zero One Knapsack dynamic programming or dynamic programming in general. So, what is dynamic programming? The dynamic programming approach to solving was formalized by Richard Bellman in the 1950s, who developed dynamic programming as a general technique for solving recursive problems efficiently. Now, dynamic programming has a cool and popular problem with a goal to determine the most valuable combination of items to include in a knapsack without exceeding its weight capacity. With this, we can apply it in a real-life scenario since, as I've said a moment ago, dynamic programming determines the most valuable combination of items to include in a knapsack without exceeding its weight capacity. Now, each item has a fixed weight and value, and the decision for each item is binary, either included 1 or excluded 0. Now, for the example that we'll use is we can line up 5 items of various weight and values and a knapsack with a capacity of 7 kilograms. So, as you can see, if we try to put all the items inside the knapsack, then not all of them would fit. So we have to be a little bit more selective as to which items we want to pick. So let's see how can we solve this problem with dynamic programming.
The first thing we'll need is a table of values to store various states in the context of the knapsack problem. We can think of a row in this table as representing an individual item and the columns as representing varieties or maximum capacities our knapsack can have. So, how we are going to solve the knapsack problem is going to be by considering the first item and then figuring out all the best possible values we can achieve for each capacity, and then after that considering the second item and reusing information we know from the first item to formulate a combined best value for those two items, and then incorporating a third and a fourth item, and etc. What we want to do for each column and the current row is figure out if we should or should not include the current item. If we don't include the current item, then we look one row above. But if we do include the current item, then we still look one row above, but shifted over by the weight of the current item, because that would be the state with the best possible value and the knapsack large enough to hold our item. Right now, item 1 has a value of 2 and the weight of 3. The weight of 3 does not fit within a knapsack of capacity 0. So the best we can do is have an empty knapsack of value 0. Similarly, for capacity of 1 and the capacity of 2. But in capacity 3, we have enough room to fit item 1. Notice that there are now 2 arrows. The short arrow points to the row above us, which represents the state of not including the current item and taking the best value from before, which in this case is 0. The longer arrow points the state in which we can include item 1 and its value to the new state. In this case, that was 2 because item 1 has a value of 2 because the next state always needs to include or not include the current item. We will label the arrow which yields the best value for the next cell to be blue. So let's keep our attention focused on the blue arrows to know which of the previous states best contributed to the new state.
Now, moving along, we can see that we increased the capacity and we are still able to include item 1 as we did before. This is because the size of our knapsack keeps increasing, so this makes sense. So the rest of this row will continue to have a value of 2 when we get to the next item. Our column is 0, so our capacity is 0 and we're not able to include any items. So we get a value of 0 right here. Next is if we consider a knapsack of capacity 1, item 2 fits into this knapsack. So we can include it, giving us a value of 2 in this cell. Moving along, we can also include item 2 for a capacity of 2. Now, something interesting happens when we consider a knapsack of capacity 3. We can either get a value of 2 from picking item 1. This is the state directly above us, or we can equivalently get a value of 2 by selecting item 2 with the diagonal arrow. So there is a tie, and in either case we'll get a best value of 2. This next state is also particularly interesting since we've increased the capacity of our knapsack to 4, so we're able to fit both item 1 and item 2 into the knapsack, giving us a best value of 4. This pattern continues on for the next couple cells. When we introduce item 3 for the first few knapsack capacities, the best value comes from the previous states, meaning the cell directly above. So this one, that one, and the state also. And now we get to a capacity of 3, and we are able to improve the best value from 2 to 4 by including item 3. We are also able to improve the best value from 4 to 6 by adding on the value of item 3 to the cell. Being pointed by the blue arrow, a similar procedure is used to fill in the rest of the row and the rest of the matrix. At the end, we finish filling the table and we can get the best value of selecting a subset of the 5 elements. We originally started with the best value we can get is going to be found at the bottom right corner, which this case is 10. So now we know how to achieve the best possible value, but we still don't know how to actually select the correct elements. To do this, the idea is going to be start at the bottom right corner, work backwards, and we include an elements. If the current value and the value in the row above, it differs. The idea being that. So if the two values differ, then the row we're currently on must have its item included. Otherwise, the value would not have changed.
Let's see an example of this. So start at the value and at the bottom right corner and look at the value directly above, which is 9. 9 and 10 are different values. So we include item 5 from the last row. Include item 5, we need to subtract its weight so that we can consider a smaller knapsack size. We doing is remove away of 2 and shift our focus where the diagonal arrow is pointing. Now we're only considering knapsacks of capacity 5 since the value of the current row for item 4 is 7 and the row above it is 6. We need to know that we also need to include item 4, so item 4 gets included, and yet we need to reduce the knapsack size and move to where the diagonal arrow is pointing. Now we're going to column 1, so we're only to considering knapsack of size 1 and the value of the current row and the row above us are equal, so we do not want to include item 3. So we can move up and not change the column. We are still only considering knapsack for size 1, so we check the value and current row and the row above which is listed. So we include item to the last item is not yet included, so 0 is 0, 0 is equal to 0. There was no change here.
So in summary, we selected 3 out of the 5 of our items. Those that are in green at the moment, that is the 4 kilogram item worth $5, and 3 kilogram item worth $3, and then 1 kilogram item worth $2. Now, we'll be showing source code for the 01 knapsack problem. The knapsack method that we are seeing is that it takes 3 parameters. The first one is the capacity of the knapsack, and it takes 2 arrays called W and V. W is the weight of the items, and V is the value of the items. So for index I, we would know what the weight would be and what the value would be. Next are check to validate some input, and in this part, we get the number of items passed in so that will be end. Then this part, this visualizes the table which we call DP for dynamic programming, and we made it one larger than we actually need. Let's do the index out of bounds species. Next, this goes through all of our items. Note that this loop is 1 base and it's not 0 base. Just because we made a table 1 base, so when we try and reach, we get the weight W and the value of the item says I, it's 1 base, we should back 1. The arrays we passed in our 0 base, so that's why this is -1 right now. Then to reach knapsack size, we consider not picking the item, so that's only at the row directly above us right now. Then it initially sets that at the best current value, and then we check if we can update to a better value by including the current item. So this would be equivalent of what those diagonal arrows in slides. Next up, this is an optional step that so the section just looks and tries to find what elements were selected. So those get stored inside item selected array, and what this do is it starts at the bottom element, and then close up and search for the items that you need. So start I at N, then increase I. This is the check that looks at the row above to see if there's a mismatch, and if there's a mismatch, we don't include that item. The index is 1 base, so we need to subtract alt 1 and then we can add to the array right here. Then we shift over the column by whatever the weight of that item was. Next, this part is just reverses the item just for the convenience, so that it corresponds to how they were passed into the method, and then it will run the list. But if we actually wanted the maximum amount, then we can just get that value by looking at the last index. And lastly, this is how we call this method. This is an example. We can base in what we did.